like home care patients.
Concentrator.
The concentrator, and what was that system?
The C.
The sieve or the sieve, right? What was it called? Molecular sieve. And what did it do? How did it work? What did it?
It takes off the nitrogen and the water.
Yeah, a physical separator, right? So it separated the nitrogen through that sieve, and then what else did it have in it? Do you remember? Pellets. And what did the pellets do? They absorbed the water, right? And so then we were left with what level of purity of oxygen?
90%.
90, only 90. Right, only 90 in that one. The medical grade is 99, yeah,
Okay.
in the hospital. So we're left with 90% purity level. And then what was the FiO2? 40, right, 40, yeah. And it could deliver flows of up to about 10 liters, right, exactly.
On our homework page, I was gonna ask about this. The first question was describe how a home oxygen concentrator provides an FiO2 of greater than 90%.
There are some adapters that you can add to them to provide higher FiO2s and flow rates. I said don't worry about that. Just you can add an adapter to some of them. You can find that in the book, in the equipment book. Okay, but I said don't, that the capability of them without that is 40% and up to about 10 liters. But you can add an adapter to some of them. Okay. And then we talked about the bulk oxygen system, and what is that process called? Fractional distillation. Good, thank you. Now that one had between 4 and 5 steps, depending on what you liked to write down, right? And the first step was to bring in the air and do what with it? Dry and filter it, right? To get rid of any pollutants that were there, okay? And then the second step was kind of a combination of steps. We were going to compress, cool, liquefy, expand. That was last. Yeah. Okay. So then we're left with liquid, right? After that step. So now we have this liquid oxygen, and then what did we need to do with it? Because it wasn't just oxygen.
We need to boil it.
We need to boil it off to get rid of nitrogen and any other gases that we didn't want. Argon was one of them.
One step, just boil off things you don't want and nitrogen.
Yeah, because you do have to tell me the nitrogen.
So
piece.
as long as we put nitrogen,
Yes,
in,
yeah.
Because
there's other gases.
That
Yeah.
was me off.
In the depiction of it, and then if you play the little video, it showed all those pieces moving, right? Nitrogen has a different boiling point than oxygen, and so it boils off first, right? And so that's how you can kind of understand that, which is, somebody who's really smart, right? So it'll boil off, and then you're left with pure oxygen, right? And then we can do what with that pure oxygen?
Send it to the cryogenic or something like that.
Yeah, we put it in cryogenic storage, and that's those big bulk systems. Cryogenic.
I feel like being frozen for the future.
Yes, I know. We are freezing it for the future. Yes, and so that's the big tanks that we see outside of the hospitals, right? And they have lots of copper piping, and they have lots of pressure gauges on them, and shut-off valves and things like that. And we talked also about how they can get iced over, right? Especially when we're using very large quantities of high flow devices, like what happened in COVID, right? Okay, and then we talked about safety systems, and First Lab has this down, don't you? You have it down, right? So Second Lab, we're gonna really hit it hard to make sure that you definitely understand all the components of the DISS, the ASSS, and the PISS, and all the pieces and how they work, right? Because remember, on this exam, I will be having equipment out, and you'll have to identify the pieces of equipment and how each piece has multiple things going on with it, right? So, because we talked about how the flow meter may have an A, SSS component, it may have a DISS on the end, and it may also have a flow restrictor as well. Yes, ma'am.
If we just want a review of those parts and stuff, is there like a page number in a book?
Your equipment book is gonna be the best resource for
Okay.
you for that, yes. You could also take pictures of any of the equipment too.
Okay, thank you.
And if you want me to label something, you know, we can do that as well,
Sounds
okay?
good, thank you.
Okay, and then we looked at flow meters, the different Thorpe tubes, whether they're compensated or uncompensated. And then remember that if they're uncompensated, there is an effect of back pressure. And what does back pressure do in an uncompensated tube?
Falsely
Low, right? Falsely low. And I love to ask questions about that, so, right? So if you're giving 4 liters and it is showing 2, are you giving 2?
No.
No, you're not giving 2. So don't turn up the flow,
Just leave it.
okay? So you can leave it, you can disconnect it from the wall to see if that fixes the problem, or you may actually have to move the patient to another room. You may report that to maintenance if there's a problem in the head wall.
So when
Okay,
And you said it would be
access
flickering, right? Like
It
going
would,
up
it
and
could
down.
be jumping up and down.
I think the book said, they don't make those anymore,
You don't make what anymore?
the uncompensated.
They definitely do make them,
They do?
yeah.
I read that they don't make one of them.
They don't make one of them
They
anymore.
don't make something, and it was one of the flow meters anymore, but they can still be found in the hospital.
They're all over in the hospital,
Yeah.
so. They could be trying to phase them out.
Yeah.
That could be possible, yeah.
I know
I was
I
gonna
read
say,
that
like,
in one of the books.
yeah, I mean, it's possible that they've stopped production of some of them, yeah. And that's because of the problem with back pressure. But they're definitely all over the hospital,
Mhm.
unfortunately.
Yeah.
Yeah. And like I said, you can tell if you snap one into the wall and when it jumps and comes back down, that it's compensated. So that's how you can check to see if it's compensated or not. So you could check them, yeah, if you're not sure whether they are or not. Because now the compensated ones, the needle valve, remember I told you that's not always at the top anymore. So that's why I always teach it that way so that you know, but that's not how they all are now. And you can see, like I showed somebody
You mean
this.
that clear one?
The clear one, yeah, the high flow one. And you can see the inner workings of it, right? It's actually on the bottom, but the valve is actually at the back. It is, yeah, it is. So that's how the newer ones are, yeah, but you can't tell by looking at it. Like, so it's kind of hard to see that. Okay, so we also talked about board-on gauges and how that those are in any device that has that pressure gauge that actually is a board-on gauge, right? So they're on regulators, they are on all of our reducing valves, and they're on our oh my gosh, my brain just what goes on our cylinders, regulators, thank you, appreciate that. And then those are also affected by back pressure, aren't they? So what happens in those in back pressure? Falsely high, that's right, falsely high, okay. They're also very expensive too. They're much more expensive than a Thorpe tube, but we do want to use those when we're transporting patients because they are not gravity dependent, Okay, and then flow resistors or flow restrictors. What's a good example of that? A Christmas tree, that's right. Because you're pushing that flow at a set pressure through the orifice. And the orifice could be different sizes. And we looked at some in lab this morning, they're all different sizes. So second lab, you're gonna be looking at some of those as well. Okay.
I got a question, 2
Yes.
questions. Cylinder, what you just say, cylinder? Oh, you said a cylinder, the regulator on the cylinder can also show a false read? Did you just say that?
Regulator on
A regulator.
a regulator on a cylinder.
Mhm.
I said a board-on gauge
Oh,
can read a false reading
Okay.
in the presence of back pressure.
But it'll
Okay.
read high.
It'll read high.
Okay.
Yeah.
reads high.
Okay. This is just another repeat of what we just said. Compensated, not affected by back pressure. Uncompensated, will read inaccurate, will read lower, right? Word on gauge measures pressure.
One more
Remember-
question,
Yes.
sorry.
Oh, you're
On
fine.
the, now I'm having a brain fart, what's the piece called?
I know, I hear you.
The big piece over there with the high pressure, regulator, the
Uh-huh.
multi. So the one that has the PSI on there, that's the boarding gauge, what would be the other smaller piece called?
That's still board
They're
on
both
gauge.
board on gauge?
Yeah,
Okay, I just
because
wanted to make
remember
sure.
that they can be calibrated for flow.
Okay,
Mhm.
Okay.
So they're both board on gauges, so, yep. And of course, again, they read higher in the presence of back pressure. Okay, the flow resistor or flow restrictor, they don't measure anything, they're not measuring flow, right? They are, they're just, pushing that flow through the orifice. Now, if you, and I didn't really talk too much about this because I don't think it's, is as important, and I'm not gonna test on this, but if you would have to have back pressure, in that flow meter, it is going to cause the flow through the orifice to obviously decrease. So if you've got something in there, it's almost like having something sort of stuck in the device itself. It will cause the flow through it to actually decrease, okay? But because it's not measuring anything, it's not measuring flow, it's not measuring pressure, it's challenging to say, well, how can it actually cause the flow to decrease when it's not measuring flow, right? So that one I'm like, I almost dispute this a little bit because it doesn't measure the flow, right? So I think just know that if it becomes obstructed in some way, the flow through the orifice will actually decrease. Okay, so that's really what they're talking about, which kind of makes sense, right? If there's something blocking that opening, of course the flow is going to decrease through it, but it doesn't measure flow, right? And that makes sense to us. Doesn't that make sense to us? Okay, yes.
but that's not on the test,
So.
No,
okay.
I don't know if this is on the test or not, but it says which flow meter does not measure flow or pressure. Would that be this?
that's this.
Okay.
Yeah,
The flow resistor?
because what it really is it's a part of the flow meter.
Okay.
So I don't know, to me, it shouldn't even be considered a flow meter because it's like an extension of
Okay.
the flow meter, right? The only reason they put it into that category is because it is a part of the regulator,
Okay.
right? It's built into a regulator. That's why they considered it a flow meter. That's the only reason why that is called that. Okay. All right, so what do you think? So Thorpe tubes are considered the most accurate flow meters, but you can't use them in transport. Board-on gauges are less accurate because again, they're gonna measure pressure, right? But they're the most expensive, of course, okay, because they have that copper inside of them. And flow resistors, they're the cheapest, right? They're the least expensive. Of course they are. They're all plastic, but they're the most inaccurate. So I don't know, which one do you want? Well, it depends on your clinical application.
Depends
what
how much
you're-
money you have.
yeah, it's true. That's true. Okay, we have talked a little bit about air compressors. Today in lab, I mentioned some air compressors within ventilators. Okay, but the thing about air compressors is that they have to be able to generate 50 psi. Because again, that's our working pressure, right? That's what we have to have to run any of our equipment. And they can come in different styles. I talked about the one that I had in the back that was on wheels that I rolled around, right, to run machines. That was way back in the good old days, right? So there are portable ones like that. There are also things like our portable nebulizers that we have at home. That's an air compressor. It's a small portable air compressor, but that's what it actually is. Now, actually, those are a little bit of a misnomer because they don't generate 50 psi. They generate somewhere around 23 to 25 psi, but they're enough to still run a nebulizer safely for home use. But we also have, again, you could think of like ones, if anybody has tools, if you've got someone in your home that has tools, there are portable compressors that are used to run some of those, like things like the ones that like blow up your tires, you know, or, my husband has like nail guns and things like that, right? So that's a portable, like little pancake compressors, you know. They make a lot of noise though. They're super noisy, and they turn air. Yeah, exactly. And they turn on and off as they will charge the line, you know. But then we have the bulk ones in the hospitals, and those would be more larger air compressors that run multiple devices in the hospitals. And then also, again, machines have internal compressors. Now, it's important for us to know whether our machines have them or don't have them, because that makes a difference if you can transport on those machines or not. So this morning in lab, I was talking to you about our ventilators, our newer servo ventilators that OSF has an entire fleet of. Those ventilators do not have internal compressors. So you can only transport if you have a tank. So you have to use an oxygen tank to be able to transport a patient safely on those ventilators. And it's a little bit scary because if your tank runs out, your vent doesn't work. And that's a freak out. So this is why you have to always take an ambu bag with you, so you have a way to ventilate your patient safely. Our older ventilators, our blue ones that are still in the back, they had internal compressors that could run safely, and so you didn't always have that concern unless your the battery died. So your battery is what charged the compressor, and it would keep your vent running for you. So you have to know and be aware, hey, does this machine have that or does it not? How am I gonna run my ventilator? So those are things that only you know as a therapist. The nurse doesn't know that. She has no idea she's just hoping that you know, right? Like, you better know, you're the one in charge of this, right? So we do have to know that information. So there's your nebulizer, okay? That's an air compressor. And it's going to be able to run that nebulizer. So that's a little portable one. Again, not quite 50 psi, but enough to run that ventilator. Oh my gosh, this is actually the one I have in my house. This is an oldie, but I probably need to get a new one. It's probably 20 years old. Hey, it still runs like a champ. If it ain't broke, don't fix it, right? Seriously, I think it really is 20 years old, at least. And there are some bulk ones, and so this looks nothing like that, right? But these are some bulk systems that are actually in the hospital to run larger pieces of equipment. So, okay, the blender. So First Lab has already seen the blender in action. So this is what we use to blend it. Generally, it's going to be air and oxygen, but it can be other gases. So we're taking two 50 psi gas sources and we're blending them to create a precise FiO2 for our patient. These are, a lot of times they are internal, so we don't see it. So it's actually inside of our ventilator and it's doing it internally for us. And then we will have analyzers also internally to be able to analyze the gas to make sure that it is precise. So when you're doing a vent setup, you will have to run through that analyzer to make sure that it's precise. And there are some safety factors, and First Lab heard the sound that it made. So what's happening is it's looking for that gas. So when you plug in one gas source to your DISS, before you plug in the other one, what sound did it make?
Loud.
Loud. It wasn't hissing, it was like an alarm sound. Ooh, right, it's a very loud sound. Because if there is a greater than 10, and this is key, you want to highlight this, if it's a greater than 10 psi difference, it's going to make that loud alarming sound because it needs that other PSI, right? It's looking for the other PSI. It's looking for that other gas. It's going to alarm until you snap that into the wall. It's going to keep looking for it. All right. So here's your blender. It starts at 21 and it goes all the way over. You got 40. I think that's 30, 40, 50, 60, 70, 80, 90, 100. 60's right in the middle. That's going to be your 1-to-1. Okay, so just like this works just like your tandem, right? So when you've got each of your gas sources. So you've got threaded connections. So threaded connections mean what kind of safety system? ASSS, that's right. So they're gonna be threaded to the right internal diameter. So you can't mix them up. Only one's gonna work for oxygen, only one's gonna work for air, right? Okay, so you'll know which one, right? So you're gonna thread those on there. So when you're at a 60%, again, you're at a 1-to-1. What's a 40%?
1 to 3.
1 to 3, good. And 100%? 1 to 0, that's right. Like, so again, you should not be able to mix up your hoses. This one's a little bit clearer. Okay, so, again, that's blending our air to oxygen ratios and dialing the knob on the front's gonna change the FiO2. Like now, when you set this up, we'll talk about this here in a second. Like when you set this up, you also have 2 flow meters attached to it. So you're dialing the blender to turn on your FiO2, and then you're gonna dial your flow meter to set the flow setting. So the flow is separate from the FiO2. Now usually you're gonna have a regular flow meter setting, and then you'll have either a high flow meter or a low flow meter, whether you're taking care of adults or you're taking care of pediatric patients, okay? So 2 different settings, FiO2 and flow. So you're gonna see that today in lab. I have one back here for you guys to take a look at. Okay, now again, because they are ASSS connections, you should not be able to connect them, mix them up. You shouldn't be able to. So this is like in a weird world where for some reason, like, you were able to do that. I don't know where, but at third shift. On third shift, everything happens on third shift. That's right. On third shift, if the oxygen pressure hose is plugged into the air and the air hose is plugged into the oxygen outlet, will a device function?
No. Won't even be able to.
It will, actually. It will function. It will. Okay? It would function. Because it has 2 gas sources. It still has 2 gas sources. So as long as it has 2 gas sources and there's no change greater than 10 PSI, it will function. You're on third shift. You can make anything work.
That's very true.
Okay?
You said because
However,
as long as it has what?
the FiO2 will be inaccurate.
No change.
That is the problem. The FiO2 will be inaccurate.
What'd you say about 10 PSI or something?
As long as there is not a greater than 10 PSI difference, it will function. It will not alarm, it will function. But the FiO2 will be different. That's gonna be the kicker. And we're gonna take a look at that, okay? So here's what's gonna happen. Okay, now, when the FiO2 is at, if you have them mixed up, if they're crossed, and the FiO2 is at 60.
More air than oxygen, so I'm gonna say it's probably gonna be higher.
Okay, so you say higher. This is a little bit of a trick question.
It is. I'm thinking of that 40 and 100 a bit.
It's gonna be the same.
Yeah.
Like, yeah, because 60 is a 1-to-1.
Right.
Yeah, so in this example, in this case, 60 will not change because it is a 1-to-1.
Right.
So if you have it at 60%, it's still gonna be 60%. Okay, so in this case, it won't change. Now, what if it is at 30%? What if it's at 30%? Yeah. Yeah, because 30 is, if you calculated it out, 30 is a 1 to 7, or should be a 1 to 7, right? Okay, but if you flip it, now you have 7 parts. You have a 7-to-1. Okay, so do your math. Do your math.
That's 10.
Like, what do you mean?
Yeah. Do your math. So if you now have 7 parts You're supposed to have 7 parts of air,
So you mean,
but
so
now you have
flip it,
7
but-
parts of oxygen,
Oh, okay, so.
okay? And you only have 1 part of air. You still have 8 parts. So you can figure this out.
%90.
That's what it is. You get about 90%. Like, yeah. So my goodness, you were supposed to be delivering 30%, and you're
wow.
giving 90%. Okay, that's a big difference. Okay. Oh, whoops! Did I jump ahead? Okay. So you can see here how I may ask something like that. Ooh, could you do it? Can you do it?
Now that you showed it.
Now
you
that I
know.
showed you how to do it.
About talking about the flip.
Yeah. So if you flip them, just do your tandem the other way, right? So if I said it was 40%, if you do it the same way, 40% so 1 to 3, but you're flipping them. So now you've got 3 parts of oxygen, 1 part of air. So you just flip it, and then you figure out what your FiO2 would be. Okay. The only time it would be accurate is when you're giving a 60%, which is a 1-to-1. That's the only time it would be accurate. So make yourself a little note of that, okay? That's the only time you would actually be accurate. Those darn third shifters, tell you what.
Right. We even go home and go to sleep.
And don't answer when you call.
Definitely don't go home and go to sleep.
Where are they? Okay, all right. The next thing I want to talk about is don't get scared. All right, something called the ideal gas law. Like now, we're gonna just dive in. We're just gonna dip our toe in this, like right now. Like, and you're not gonna have to do any calculations with this. Okay, for this exam, no calculations. Why? That's right. That's right. I do. Okay. Like now, that's gonna be coming, but not right now. Okay. We're just gonna dip our toe. Just
My
dip it.
SpongeBob when
Yeah.
he's driving.
Yeah. Yeah. Yep. Exactly. Like so. So what we're gonna be talking about is the relationship between 3 variables. Okay. Pressure, volume, and temperature.
Was
That's
coming
it.
down?
Yes, it is. But just the toe dip, okay? Just the relationship between these 3 variables, pressure, volume, and temperature, okay? So the gas law says, okay, so we're gonna have 1 on one side and then always then what happens on the other side. So we've got this, so don't let this scare you. In fact, can I erase this, y'all?
Yeah, I took a picture of it.
Okay.
if anybody needs it.
And I don't like, when I have to do equations like that, I don't like it, it's hard to write it like that. I like it better like this. Okay, because what they're saying is this, and T1 is always gonna go on the bottom. Your temperature is always gonna go on the bottom. That's gonna help you right there, whenever you're writing these out, okay? All right, so what they're saying is you've got a relationship between pressure and volume and temperature over here. So you're starting with pressure, whatever your starting pressure, volume, and temperature is over here is gonna equal your new pressure and volume and temperature, okay? So what you start with and then your new pressure, volume, and temperature, right? So that's what all this is saying, and this is just telling you where they go in the equation. So typically we're looking at two at a time, okay? But when you put them all together, this is just showing you, do they have a direct relationship or do they have an inverse relationship, okay? And only one has an inverse relationship, and the other ones all have a direct relationship. Meaning direct, they have, when one goes up, the other one goes up. One goes down, the other one goes down. That's a direct relationship. But when we say inverse, we mean that when one goes up, the other one goes down. Or one goes down, the other one goes up. That means an inverse relationship. Okay? So let's take a look at what that means. Okay, but this is the ideal when they're all together in one. But we can divide them all up, right, into separate equations. Okay, because when we pull them apart, we tease these apart, then we're going to be looking at, okay, something's got to be constant, and then we have the other two variables. All right, so I'm going to kind of show you an easy way to remember this too. So the first one we're going to be looking at is Boyle's law. Boyle was a very important guy, and he plays a huge role in respiratory therapy for us, okay? This is Boyle's law. Now you're seeing something missing from Boyle's law. What's missing out of these?
The temperature.
The temperature, okay? Because that's what's constant in Boyle's law, okay? Remember I said when you pull one thing out, you tease it out, that's what your constant is, okay? We got three things. What you don't see that's missing is what's held constant, okay? So temperature is missing, all right? So that's what's constant. Okay, so temp is constant in Boyle's law. And you can remember that because you've got a T. TB. Oh boy, nobody wants TB. That's terrible. Nobody wants tuberculosis, okay? Just remember that, TB. Temp constant, okay, in Boyle's law. So pressure and volume are what is left here, all right? So you've got a P1 and a P2. That's what's on top, okay? This is the only one that is inverse, is Boyle's law. The only one that's inverse, okay? And so when it's written like this, that means it's inverse. Okay, so Boyle's law says that when pressure goes up, volume goes down. Or conversely, when pressure goes down, volume goes up. And we have already learned this actually, because when we talked about how when you're flying with patients and they have an endotracheal tube in, you know where I'm going with this, right? And it has that cuff on it that's filled with the volume of air. And we take them up in the atmosphere. We go up in the atmosphere, pressure does what? Pressure goes down, right? Remember my little drawing? First day of class, sitting on the little mountain, right? Pressure is down. So if pressure goes down, the volume in that cuff is gonna go up, and it can burst, right? So that's important for us as respiratory therapists to understand. So I need to pull volume of that out of that cuff so it doesn't happen. And then when I bring them back down to the ground, I need to put the volume back in because the pressure now came up. I brought them back down to the earth, right? Pressure came up, so now volume is going to go down. There's an inverse relationship there.
Is this like if we transfer them on like?
Yes,
like
yes,
okay.
yeah, in the helicopter, yeah, okay? So there's an inverse relationship here, okay, of pressure and volume, okay? So, that's showing you here a little balloon. Does it show something else? Yeah, there we go, all right. So when I took the pressure down in this container, I'm sorry, yeah, the volume went up. The volume expanded here, okay? And then here, this one was taking the pressure up and the volume went down. I don't really like that depiction so much. I've got more of these, okay. Just think about, I think that one with that going up in the helicopter and the ET too, I think that's a better understanding for all of us. Okay, so remember that one. Remember the helicopter, remember the ET too, the volume. Okay, all right. Okay, all right, so our next one here, we've got, so the next two are gonna be direct relationships. This is the only one that's inverse, okay? The only one. Our next one here, you see temperature and pressure. What's missing?
Volume.
Volume. Okay, so volume is constant. All right, so this is Gay-Lussac's law. Gay-Lussac's coming to the party. Woo, welcome. Gay-Lussac's law. We haven't talked about this guy yet. Okay, so volume is constant.
One question,
Yes,
cause it sounded like you just said this is the only one that's inverse. I thought you just said.
this
that
is the
one-
only one that's inverse.
Oh,
Boyle's.
Boyle's law. I'm sorry,
Boyle's
like-
law
Okay.
is the
gotcha.
only one that's inverse. So.
Okay.
Okay, so now we've got P1, T1, P2, T2. Remember I said temp's always gonna be on the bottom. That's gonna help you. Temp's always gonna be on the bottom. Okay? So, when pressure goes up, temperature goes up. Okay? When pressure goes down, temperature goes down. Or you can think about when temperature goes down, pressure goes down. And this one, I always think of, I do think of balloons when I think of this one. Like, if you ever gone to go pick up a bunch of balloons and it's been cold outside, they go down. Or if you've had balloons in a hot car, they pop up. Because this has actually happened to me. And I'm like, what? Oh, what happened to my balloons? For real, it's happened. Like, I picked up balloons for a graduation pinning ceremony, and they left them in my car just for a very short time. And I was loading, and I came back, and 2 of them had popped. And I was like, you've got to be kidding me. Because it was really hot that May. Like, okay, so, and there we go. Look, there's the balloons. Temperature went down, it got cold outside, you took them outside, and it went down. And I always, and sometimes I've done this before on Respiratory Care Week. The timing didn't work out this year with the curriculum, but like I bought balloons for Respiratory Care Week, and we've all gone outside in the fall. But this fall it was ridiculous, and it was 90 degrees, so it wouldn't. Well, maybe it would have worked. Maybe it would have popped it. I don't know. But sometimes we'll go outside and watch the balloons then go down. Like, so you got to think about it like that. So think about balloons and Gay-Lussac's law. I don't really have a good one for that's not dirty for Gay-Lussac's law. So use your imaginations. All right, so our last one that I want you to know is Charles' law. Charles' law. Okay, seriously, you're all adults. All right, Charles' law. Okay. Charles' law.
So is the pressure constant with this one?
You got it, girl. All right, because that's missing, right? There's no P. Charles' law. So we've got pressure constant. Now this one is also easy, I think, to remember here. Okay? Because you've got CP. Nobody wants CP either. That's terrible. Okay? Nobody wants that. All right. So that's missing. So now again, we've got a direct relationship. Okay, so we've got volume on top. Remember I said temp always goes on the bottom. Temp always goes on the bottom. You will never wreck yourself. Can you see, girl? I'm sorry. It's like coming down. Okay, you see, is my stuff probably in the way? You're like, it's getting low down there. Like, all right, so again, and it's sort of related to the other one, right? So when temperature goes up, the volume goes up also. So the volume in that balloon goes up, right? Which will also make it burst, okay? And then again, when temperature goes down, that volume also goes down. So those are very much in relationship with each other. Okay, so these I don't think they're too terrible, right? Just memorization right now, okay, with these. So again, this is your ideal right here when you've got all of them up here together. But then when you pull some of these pieces out and you're looking at what is the relationship and then what's constant, okay? This is the inverse, the only one that's inverse. It's even written different, right? Because it's going to be a multiplication, okay? Actually, we're actually gonna be dividing. We'll talk about that later. Don't worry. Don't worry. Don't worry. Don't worry right now. We're just dipping our toes. Okay. Okay. And then you've got direct. So for this exam, this is all you need to know. Okay, what is explaining the ideal? You've got three variables, the relationship between three variables, okay? Boyle's law, pressure and volume, inverse relationship, temp is constant. Gay-Lussac, you've got the relationship direct between pressure and temperature, volume is constant. Charles, our man Charles law here, pressure is constant. Again, direct relationship between volume and temperature. Okay? That's all you need to know for right now. Again, we're just dipping